Hello and welcome to Starfish Maths. My name's Sarah and today I'm looking at proof by contradiction. This follows on from my other video I made on proof, so it might be worth watching that one first if you haven't already. I'm going to work through 5 examples and some of them, the first 2 or 3, you might like to have a go at yourself, and then the last couple are famous proofs which it might be worth you knowing those ones off by heart. As ever, please do grab a pen and paper and write notes or have a go yourself, pausing the video, rewinding as you need to. Some of them you might want to work through them more than once. Please do let me know if this is helpful or any other feedback in the comments below, or get in touch at starfishmaths@gmail.com. You can ask me about masterclasses or online tuition. If you're ready, let's get started. Okay, here we have our first example. Now, proof by contradiction is very powerful. But it can take a little time to get your head around. And the way it works is you take a statement, and to prove that it's true, you assume the opposite. You assume the opposite of the claim is true, and then show that that doesn't work. So you assume the opposite and try and arrive at a contradiction. So hopefully you'll get the idea as we work through some examples. Here's our first one. If P and Q is irrational, then at least one of P and Q is irrational as well. So what is the opposite of that claim? The opposite is, if P and Q is irrational, then P and Q are both rational. So we're going to assume that and try and arrive at a contradiction. If you watched my first video, I reminded you what irrational means. If numbers are rational, then they can be written as a letter over a letter. They can be written as a fraction. So if we're assuming that P and Q are both rational, then they can both be written in that form. So here we're assuming the opposite of the claim. So we're assuming that both P and Q are rational. And what that means is P can be written as something over something, and also Q can also be written as something over something. So I'm going to use 4 different letters, whatever letters are fine you can use. Then it's talking about P plus Q is irrational, so we're going to try and break that. We're going to try and get a contradiction there. So P plus Q, using those letters, then using some algebraic fractions, you can write them over the same denominator. So multiplying the first fraction by D and multiplying the second fraction by B to get the denominator of BD. Now that is something over something, so that is rational. So that proves that P plus Q here is rational. But here we have in the statement it says P and Q is irrational. That is the contradiction. So when you use proof by contradiction, you assume the opposite, get to a contradiction, and then at the very end you can conclude, therefore P and Q are not both rational. Or whatever words you want to use there to say that, yeah, it must be that at least one of P and Q are irrational. Okay, here's our second example of proof by contradiction. So this statement, for all positive x, x plus 1 over x is greater than or equal to 2. Again, we're going to start by assuming the opposite of that. So we're going to assume that x plus 1 over x is less than 2. So we're assuming the opposite and hopefully arrive at a contradiction. So looking at this algebra, I'm going to get rid of the fraction by multiplying by x. Now, one thing just to be aware of there, if you're multiplying by a negative number, then the inequality sign flips. But here we know that x is positive, so we're fine, it can stay that way round. Now I'm going to pull that term over to this side of the inequality. So you've got minus 2x plus 1. And show that that is a contradiction. So we've got a quadratic there, and using various methods you could sketch the graph of that, or you could complete the square. So we could turn that into that. And either by sketching the graph and showing that it's never negative, or by doing that we can show that is a contradiction. If you saw my last video on proof, I talked about this before. Square numbers are always positive. So because that's a square number, it has to be positive, so it can't be less than 0. So that is a contradiction right there. So we can therefore conclude that this has to be true. Okay, third example. Here we've got for all integers, so integers are whole numbers, a and b, a squared minus 4b, it can never equal 2. We're going to start, same as before, by assuming the opposite and hope that we find a contradiction. So the opposite of this statement is that it does equal 2. Now the way we're going to tackle this is by using a method which you might have seen if you've done the proof that root 2 is irrational, which we're going to cover later actually. But we're going to pull the minus 4b over to that side, and then 2 is a common factor of that. So that means that a squared is even, because if you've got a factor of 2 then it must be even. And if a squared is even, that means logically that a is also even. If a is even, then we can let a be 2 times another number, where that number is an integer. And then we can put this back in to where we started, so substituting that back into the beginning here, 2m squared minus 4b, expanding that out, and now we can halve all of that to get 2m squared minus 2b equals 1, but I could pull 2 as a factor out of that again, equals to 1, and that then says that if m squared and b are integers, then this is even, which means that 1 is also even. Therefore 1 is even, and that is a contradiction. So then we can prove that it never does equal 2. So that proof and the next two are ones that if you've not seen them before, you wouldn't really be expected to come up with them yourself. I mean, looking at that you might think, I'd never in a million years come up with that idea, but once you've seen it, then if you are given something else that's similar, you might be able to use that again. So it's just picking up tools and tricks as we go. And I'm going to finish this video today with 2 proofs that are quite famous, and the proofs were made by quite famous mathematicians down the ages. So you're absolutely not expected to come up with these yourselves, but they're good ones to know and good ones to remember. So here is one of the famous proofs we're going to look at, and this one kind of blows my mind actually. The statement is there are infinitely many prime numbers. Now if you didn't know how to use proof by contradiction and didn't know this method, how on earth could you go about proving that? And that is the staggering power of these proof methods, that you can prove there's an infinite number of things. Quite incredible. So we're going to assume the opposite and arrive at a contradiction. So the opposite of infinitely many prime numbers is that there are a finite number of prime numbers. So we're going to start off by assuming that. So we're assuming there are a finite number, and I've called that number n. A finite number n of prime numbers. So that means those prime numbers can be listed and ordered. So what we can do is label them P1, P2, all the way up to Pn in order. And then here's the clever part. Then we define another number, which I'm going to call capital P, and that is made by multiplying all of those together. So we're going to multiply all those prime numbers, so they're all the prime numbers that exist, and we're multiplying them together to make another number, but we're going to add 1 to it. And now we use some logic. If a number is not prime, then it must have factors, and those factors can always be broken into prime factors. You can do a prime factorisation of any number. But here, all those factors are in this bit. So this number is made up of a number that has all the factors in it but plus 1. So in other words, whatever number you divide by, you'll always get a remainder of 1. So that means that this number here must be prime. But that's a contradiction because we said that this was a full exhaustive list of all the prime numbers, and that one didn't include our capital P. So what we're saying is, if there's a finite number of prime numbers, if we can list them all, but then no matter what that list is, if we multiply them together and add 1, we can always create 1 extra, and that is a contradiction. So therefore we have to conclude that there are infinitely many prime numbers. Isn't that clever? Okay, we're going to finish today with a classic proof, root 2 is irrational, and this is one that you need to know off by heart so you can learn this proof. Hopefully if you understand it well, then you can follow the logic through yourself and derive it again. And we're going to use proof by contradiction. We're proving that root 2, and you can do this for any number, root of any number, a third, is irrational. So we're going to assume the opposite and get a contradiction. So the opposite here is that root 2 is rational. And as I've said before, a rational number can be expressed as something over something. So we're going to say root 2 is P over Q. And then the really important bit here is to say when you've got a fraction, you can always simplify it down. So we're going to say that P and Q are in their lowest terms. And what I mean by that is there's no common factors. So if P and Q was something like 6 over 9, then you could just simplify that down to be 2 over 3. So we're going to assume that they are in their simplest form. And that's the most important bit of the proof. That's the whole crux of the argument, because that's going to give us our contradiction. So what we're going to do is multiply the Q up to that side to get P. Then we can square both sides. Now here we've got 2 multiplied by something, which means that that's even. So that means that P squared is even. And if that's even, then P has to be even too. Now if P is even, then we can write it as 2 multiplied by something else. So we can replace that here. And I've just multiplied out that bracket. Now we can cancel 2 on both of those sides to get Q squared is 2m squared. Now that's 2 multiplied by something, so that means that that's even. Q squared is even. Which means that Q is even. Now look at these. If P is even and Q is even, then they're not in their lowest terms, because if they're both even, then you can halve the fraction. So that is your contradiction. And that's how you prove that root 2 is irrational. I hope that was helpful and gave you some good tips. And keep practicing proof by contradiction and have fun. Thank you so much for watching.